Yeah, it doesn't matter. Oh, thank you for the invitation. It's my second time being in Florence. It's a beautiful city with a heritage of culture and physics. Yeah, today I talk about the spin polarization. Uh, yeah, sorry, spin polarization and spin alignment in heavy ion collisions. How to how to yeah. Firstly, I will talk about the here or here is the angle. Yeah, I talk about the microscopic model for spin vorticity coupling that can emerge from the spin orbital coupling in proton-proton scatterings, and then I talk about the global and the longitudinal spin polarization in heavy ion collisions with emphasis on the solvable Brustwave model. Then I will talk about the spin Boltzmann equation or the spin kinetic equation for massive fermions and vector mesons. Then finally, I will talk a little bit about the spin alignments of the vector mesons. As we all know that the star carry out the first measurement of the global polarization of lambda hyperons. Here is the measurement, the result, P lambda as a function of the collisional energy. You can see the polarization of the lambda is about a few percent at low energies, while it's almost zero at high energies. Why the polarization of the lambda can be measured is due to its parity violating decay. For example, the lambda can decay to the proton and the pions, and the momentum of the proton favor the direction of the spin of the lambda in its rest frame by measuring the momentum distribution of the proton, delta proton, in the rest frame of the lambda. One can extract the spin polarization of the lambda. So according to this data, imply that the angular velocity or the vorticity of this fluid can reach 10 to the 21st per second. This is the largest angular velocity that has ever been observed in any system. And here are a list of some review articles in this field. Some articles put emphasis on the phenomenology, and the others put the emphasis on the theory or both. So this is the latest, to our knowledge, this is the latest review articles, and will be, has been published in this journal as a book chapter to QGB6. Then I talk about the emergence of the spin vorticity coupling from the spin orbit coupling. Then we consider a very simple model. Quark scattered by a potential, static potential, with a small angle scattering in static potential described by this in the momentum space. Here, mu is the screening mass, which is proportional to the temperature. You can see when you assume that this spin polarization, spin quantum direction is n, is denoted by n, then with the momentum p of the parton scattered in this potential, then you can write down the polarized cross section at the fixed impact parameter xt, which is proportional to n dot xt cross p. P is the momentum of the quark. Xt is the impact parameter. So you can realize that it is nothing but the spin orbit coupling. And this n is denoted the spin quantization direction. So this is a static potential scattering of the quark. And we can consider a very more realistic scattering, 2-to-2 scatterings of the quarks. If we consider the collision of particles as a plane waves, one can see this is two incoming particles which carry on lambda 1, lambda 2 spin states. Well, it's scattered to the final state particle, also in plane waves. If we sum over lambda 1, lambda 2, lambda 4, and keep the lambda 3, the spin state of the one scattering particle in the final state open, then we will see this. There's no polarization because the spin up, the differential cross section of the spin up is the same as the different cross section of spin down, because there's no definition of the initial orbital angular momentum for the plane waves. In order to introduce the orbital angular momentum in the initial state, we have to consider the collisions of particles as a wave packets. For example, this is a wave packet. It's a two incoming particle as a wave packet, because wave packets has a feature that it is localized in the transverse plane. So therefore, you can define the impact parameter B. So due to this orbital angular momentum in the initial state, we can see if we look at the the polarization of the one particle in the final state, we will see that it's not the same. So there's the polarization of the final state particle. So this is due to the spin orbit coupling, because in the initial state we have OAM. Then it will convert it to the polarization of the final state particles. Okay, so then we can write down the formulation. For example, this two quarks scattered to two quarks. If we keep this lambda 3, the spin state the lambda 3 open, then we can calculate the polarized differential cross section. And here you can see this energy momentum conservation, and there's a final state, the momentum measure of the final state. Then this is a flux. This flux factor is F. C is the color factor. So because we have four delta functions for the energy momentum conservation, then we can integrate over P4, the momentum of the one final state particle. Then to remove these three delta function for the momentum conservation. Then we can also integrate out another momentum component, let's say P3Z. The P3Z we can integrate out by removing the last delta function for the energy conservation. Therefore, we remove this. The delta function has been removed by integrating over P4 and the P3Z. Okay, so then this is a result in this formula where there's only the perp, Q perp is left. You can see this, in order to derive the differential cross section at a fixed parameter, impact parameter, then we insert this this identity, dxt and dkt with a phase factor here. We split this mq star by mqt and mqkt, because once you carry out this, which give you the delta function requiring the qt equal to kt, therefore you can come back to recover the original formulation, original formula. Then therefore we remove this integral and put this dxt to the left hand side. We get this the polarized differential cross section at the fixed impact parameter xt, which is given by this formula. There's dqt, dkt with a phase factor as mqt, mkt star, while this lambda we can split. split this factor into two parts. One depends on QT, one depends on KT. So therefore, we get this differential cross-section at the fixed impact parameter xt. If we integrate over this xt to the whole plane, the full the angle from that means the azimuth angle phi from 0 to 2 pi, we get this sigma up equal to sigma down. It's nothing, nothing new. But if we integrate over the xt to in the upper plane, upper space, so therefore there's a xt is on average xt pointing to up direction. Therefore, we can realize this as a spin up cross-section is not spin down cross-section. So this gives you the polarization of the final state particle. So this is the polarized differential cross-section at the fixed impact parameter xt is nothing but the proportional to the spin orbit coupling. Okay, so then this is one scattering. In order to get the observable, the obtained observable comparable that can be compared to experiment, we have to take ensemble average. Because this is a thermal medium, so all the particles are pointing to the different directions. If we consider the scattering of the particle located at the xa, the position, scattered with another particle which is located at xb with momentum pa and pb. Then, but this is what they looks in the left frame. Then we can transform this to the center mass frame, while this the position of the xa becomes the xca. Position of at the xb becomes the position at xcb. This is the center mass frame. While the PA becomes the PCA and PB becomes the PCB. And the PA, PCA, and PCB is with the same magnitude but the opposite direction. So this is what they look in the center mass frame, the scattering. So because there are two incident particles which is located at XA and SB, different space-time points. Therefore, if in the left frame, the collision time TA equal to the collision time TB. Because the XA is not XB, therefore the time of the collision for TA for the A particle is not the time for the B particle. Therefore, in order to let them collide, so we impose the causality condition in the center mass frame for scattering particles of at two different space-time points. That is, the time interval and the longitudinal distance of two space-time points should be small enough for the scattering to take place. That is, require this delta Tc in the center mass frame equal to 0, delta XCL equal to 0. That means the collision takes place at the same time and the longitudinal position, but displaced only by the impact parameter. So this is the causality requirements for two scatterings happens at the two different space-time. So this is the quark polarization rate per unit volume. It's involved. Is dp dx4. This is a rate per unit volume, which you can prove with a very complicated. Sorry. Yeah, it is a non-local collision. Yeah. It's not the classical. It's just the non-local collision. Yeah, it's a non-local collision here. Yeah. Yeah, semi-classical. I would say this is not the purely quantum, but the semi-classical. It's you recognize the momentum and the position at the same time. It's a wave packet. It's a wave packet. Yeah. Yeah, this is another issue. It's another issue because this is a requirement we put by hand, because it is according to the, for example, if two particle in collision, they are located at the by a very large distance, they cannot collide, right? So because in the quantum field theory, in the textbook, any textbook quantum field theory, the collisions only you can describe the collision or the scattering in the plane waves, the momentum state. Two momentum state collide, then becomes two moments in the final state. So this is purely there's no position, right? But in order to obtain the vorticity, spin vorticity coupling, you have to deal with non-local collisions. The non-local collision, that means there's a collision take place at the two different space-time points. Okay. Here you see, I only require this the delta TC. The time is the same, but the longitudinal position is the same, except in the transfers. They differ by impact parameter. The B should not be large enough. Should not be large. Otherwise, they cannot climb. Because this is the wave packet. The size of the wave packet is very small. So therefore, you have to impose that the B should not be large. Otherwise, they cannot climb. Yeah. For example, yeah. What? P wave. It's not just a P wave, any, because it's orbital angular momentum. You can make expansion with respect to the harmonic spherical harmonic function. There's maybe S wave, P wave, D wave even. So it's a lot of decomposition, a lot of components. Yeah. You can estimate, because the OAM is just B times P, right? B times P, if the B times C is larger than H bar, there's at least this unit of the orbital angular momentum. Yeah, here is just a classical picture. Yeah, quasi-classical picture. But I mean, you can recover the H bar. Okay, so this you can show that with a straightforward, but it's complicated. You can show that this is a quark polarization rate per unit volume is proportional to this. This is a partial beta u rho. It's a flow velocity. Is a gradient of the flow velocity times a tensor. This tensor involves the 16 dimension integrals. So this is a post-numerical challenge. We have developed the ZMC integral, a Monte Carlo integration package that runs on multi-GPUs to tackle this problem. Another challenge of this problem is that there are more than 5,000 terms in polarized amplitude for squared for the 2-to-2 pattern scatterings. So all these you can. This is the numerical result. For example, if we focus on the y direction polarization, this coefficient is proportional to B naught. B naught is the cutoff of the order of hydro length scales 1 over the the partial U, and larger than the interaction scale, this inverse of MD. So you can see that the quark, the quark gluon scatterings and the quark scattering dominates of this polarization of this W, the polarization coefficient. And this is can be this is a W is just here. It's the coefficient, which is tell you that this is the polarization production rate per unit volume is proportional to the vorticity. This is the emergence of the spin vorticity coupling from the spin orbit coupling. Okay. B0 is just the cutoff because you see there's a divergence. You limit this. For example, this if the B0 is too large, then this this scattering, non-local scattering cannot happen. So it's just a cutoff, the upper limit for this impact parameter. For example, if the B0 is very large, and this is the rate very large. In order to determine how large it is, you can compare it with the data. Data show this be not something like 3 Fermi. You cannot be larger than 3 Fermi, otherwise it's contradicted to the data. Okay. Yeah. Mm-hmm. Yeah. This is show how to get this coefficient from the microscopic scattering, non-local scattering. Yeah. Yes. This is the upper limit for the impact parameter. Yes. But this is yeah. Maybe we can talk after this talk. I think it's very interesting. So to determine the B naught, if you have some way to determine the B naught from the first principle, that would be very good. Yeah. Yeah. Okay. So then from the spin vorticity coupling, you can calculate the polarization vector from this this is the phase out formula. This is I think this p hat is the operator, and the p is the average value. So this is the vorticity. This is the thermal vorticity because the beta is inside the gradient. So using this freeze-out formula, we can calculate using the we can simulate the vorticity, the field, the vorticity, using the either transfer model or the hydro model to get to calculate the global polarization as a function of the collision energy. You can see a lot of model can reproduce the data very well. This show that this is a global polarization is kind of a robust effect. No matter what model you use, you can always describe this using the spin vorticity coupling. Okay, so then comes a problem, and Francesco's group first found this puzzle because if you use the hydrodynamics, you can prove that the PZ is some kind of minus sine 2 phi. For example, is for the first correlation you get negative, positive, negative, positive, and later we confirm this Francesco's result using the transformer model. When you can see this positive, the negative, negative, the first correlation, negative, positive, negative, positive. So using the transform model. So this is a puzzle, but it is contradictory to the data. The data show that the data show is a sign. There's a sign difference. Also, as a first attempt, in this paper, we propose to test this sign using 4 different kinds of vorticity tensor. The first one is the non-relativistic vorticity. The second one is the kinematic vorticity, and the third one is the T vorticity, temperature vorticity, and the last one is frequently used, normally used is the thermal vorticity. We can see that only the T vorticity can reproduce this, has the correct sign. Okay, so then Francesca's group and Yin's group, they proposed another solution that is the shear-induced polarization. This is a shear tensor, thermal shear tensor, and you can introduce a unit, the time-like unit vector, T nu, then contracted the P rho with the Y index of the shear stress tensor, then contracted with the antisymmetric tensor. Then you get this P eta, the induced, shear-induced polarization. Then it seems that you use this, then you can get the crest sign. But it is unfortunately, this is Ian's group. Unfortunately, if they use the polarization of the S-quark, they can seem to get the correct magnitude. But if they use the lambda polarization, you can see it cannot reproduce the data. Okay, so then this is not only the harmonic, not only the n equal 2 harmonic can have this sign behavior. Another is the n equal to 3 harmonic also show the similar behavior. And I think as the star collaboration just try to explain such a sign to phi behavior by using a Brunswick picture. It's simple. If you look at this plot, you can see it because of V2, the elliptic flow. Then the flow velocity is this is the profile of the flow velocity. You can see that there's a gradient. There's a gradient of the px in the py. So therefore, it indicates that. So this the pz should be the positive, negative, positive, negative. So just consistent with this what experiment observed. So this is a very naive estimate. If you write the v velocity, flow velocity, as there's a radial flow, and there's a v2. There's the elliptic flow with cosine 2 phi. Then immediately, if you calculate pz as a partial x vy minus partial y vx, it immediately get the sine 2 phi behavior, but with the correct sign. So this is inspire us to look closely at the Brunswick model. So therefore, we have found a solvable Brunswick model based on this f, this distribution function. Actually, we assume that the distribution function is the Boltzmann distribution. While this p, you can express p in terms of the rapidity. This is the momentum rapidity, and pt, the transfer momentum. Phi p is the azimuthal angle of the momentum. Then you can express the flow velocity in terms of the space-time rapidity and the transverse rapidity. And phi b is the emission angle in position space, in coordinate space. Therefore, you can see this f is just related to the eta minus y, the difference between the space-time rapidity and the momentum rapidity. And also, it depends on the phi b minus phi p. Phi b is the emission angle in the coordinate space, and phi p is the azimuthal angle in momentum space. Therefore, we name this, we call this correspondence as a flow momentum correspondence, which is related to the eta to y and phi b to phi p. Okay, so about the transverse expansion, this transverse expansion can be described by the transverse rapidity, which is in this form. R tilde is proportional to R, the radius. Then the rho 0 is the constant. Rho 1 is related to the direct flow, give the direct flow, and the rho 2 term gives the elliptic flow. And if we assume that this is an emission area, emission transverse area. Emission transverse area. If the emission transverse area is a very deviate from the circle by a small amount, the deformation is very small. So therefore, we can expand this is R tilde with respect to this eta. Eta is the ellipticity parameter of the emission area. Okay. Yeah. What I don't understand is, for example, you take Francesco working with painful, so they do the full hybrid, which is supposed to be better than the plastic. Yeah, and usually, unexpectedly, when you look at longitudinal polarization, this is mostly driven by the acceleration, and not by the. Because if you look at what are the contributions which drive responsible for the polarization of the longitudinal. You look at this, mostly acceleration. Yeah. So vorticity, so this kind of vorticity, like derivative of x, what is the meaning of it? Last week's picture. Yeah, Brazil picture used in the STAR paper, and they just want to understand what about the sun. It seems very straightforward. Yeah, because it's too simple. Too simple. It's too simple. Because this is there's some relativistic effect. Because this is a non-relativistic approximation to PZ. There's another contribution from the space-time derivative acceleration. As Francesco said. Yeah. So this is very too naive because but it's inspires us to look closely at this problem. So we solve this by using this Brussels model. Then we can really solve it. So this is our main result. So in the leading order of the flow momentum correspondence, that is eta equal to 0 equal to y, and the phi b equal to phi p. Then we can derive the analytical result for p omega and p eta. P omega is a vorticity induced polarization and shear induced polarization. For example, so this is a p omega along the y direction. You can see both p omega and the p eta along y. Y direction is the direction of the OAM. Then it is driven by the direct flow, a proportional direct flow. Well, you can see the phi, the azimuthal angle dependence is a cosine square phi p. It's exactly what experiment observed. So we will show later. And if you look at the longitudinal polarization, p omega and the p eta along the longitudinal direction, you can see that it's driven by the elliptic flow and the ellipticity in emission area, epsilon. So, and it's the azimuthal angle dependence is just the sine 2 phi. And you can see the sign is correct. So this is actually you can solve this Brussels model analytically to get this solution. Okay, so then just the numerical calculation using that for, analytical formula. Then this is the result of PZ and PY as function of the phi p. You can see it's a perfect. It's a perfect match the data. So this is a sine sine 2 phi, and this is a cosine square phi p. So exactly you can see. So this is the phi p. Okay.
In this calculation.
Yeah. Was it? Yeah, this is a negative, but share is a positive. So it's larger than this. Yeah. 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 It's impressive because it is a Brussels model. Yeah. Star, yeah, it's reasonable. If you calculate it exactly, you get this. What? Huh? Oh, yeah.
But it led to a wrong prediction because the vorticity.
Vorticity is a negative. Yeah, exactly. Yeah, exactly. This is the difference because this is a relativistic effect. Then the star argument is a non-relativistic effect. So therefore, if you take the relativistic effect into account, you will get wrong sign. You will get wrong sign. Yeah. Acceleration.
The message is that a better motivated Blackwell model leads to the same result as a hard analysis.
Yeah, exactly. Yeah. So this is no, don't make mistake. It just inspire you to think about this, right? This is just the argument. They put the argument there. It's just the argument. No temperature gradients. I will show you. No temperature gradient because you see, there's no temperature gradient. Only this. No temperature. But temperature gradient is 0. You can calculate the profile. Then you can prove that 0 for the Brussels model. Thermal half surface, yes. Okay. Yes. Acceleration is a purely relativist effect.
Okay.
Yeah.
So, for example, how much should I accelerate to polarize the area?
Yeah, you have to ask.
The ratio H is H bar G divided by H bar G divided by square.
Yeah. Okay. Yeah, we just draw the figures, our result. You can see, I think most of the hydros calculation or the transform calculation, they did not get this very well because sometimes they use this. Yeah, this is a perfect because the curve itself show that it's a cosine square phi. It's we get it from the analytical solution. Right, it's a cosine, cosine phi. We get this. And the coefficient just match the magnitude of the data because we can tune the parameter in this function to get the data. Very well described. So, what? Yeah. Yeah, we have a free parameter. You see the parameter alpha 1, you see the alpha 1, is can be described by the directed flow. Is correspond to the directed flow, and the rho 2 is correspond to the V2. But they are constrained by the flow data. Yeah, it seems that there's no free parameter. There's free parameter. Everything is consistent. Yeah. Okay, so then we can calculate the PZ as function PT and the PY as function PT also match the data very well. You can see for the global polarization, I think the dominant effect from the vorticity polarization, not from the shear. But for the PZ, it's almost the magnitude are the same from the shear and from vorticity. Also, we can calculate the PZ as function of centrality and PY as a function of centrality also match the data very well. And if you go to the very high energy, for example, the ARC energy, you can see PZ as function of centrality and the PZ as function PT almost perfect. There's a perfect agreement between the data and the Brussels model results. Also, this is at the ARC energy, the global polarization almost zero. It's because it's a very high collisions. The PY is almost zero. Okay, so then here's a summary of the features of this model. This is an analytically solvable model for spin polarization based on the Brussels picture of heavy ion collisions with flow momentum correspondence at the leading order. Then it not only gives the exact azimuthal angle dependence of the spin polarization in the beam and in the angular momentum directions, but also gives the exact transverse momentum dependence. Here, there's no temperature gradient contributions because we assume that TF is a constant on the Fresnel hypersurface. It can describe almost all available data for spin polarization with a few parameters constrained by the transverse momentum spectra and the collective flow of hadrons. And it can be improved order by order through the expansion in the delta phi. Delta phi is just the phi b minus phi p, and the delta eta. Eta is the eta minus y. Okay, so this is the first topic. I turn to the second topic is the quantum kinetic equation with spin, or the spin Boltzmann equation, spin kinetic equation with Wiener functions. Okay, so for the spin 1/2 particles, you can define the Wiener function, which is a 4x4 matrix for defined from the field of fermion fields. One field is located at x plus y over 2. The another is located at the y x minus y over 2. Then by Fourier transform with respect to the y, then you get the Wiener function, the phase space distribution, which is a 4x4 matrix. And then you can decompose this Wiener function in terms of the 16 generators of a Clifford algebra, namely the scalar and the pseudoscalar, vector and X-ray vector, and the tensor. From these components, you can get the vector current and the axial vector current and the T min nu. And so you can define the spin-dependent distribution from this Wiener function. It is defined through the operator, the A dagger, which is Rs, denote the spin state of the fermion, and the P1, P2 it's the momenta. If you Fourier transform with respect to the Q, Q is the difference between the two momenta, then you can get the so-called relativistic metric value spin distribution, F. Here is Rs is denoted the spin states of these two operators, which is a 2x2 matrix. So you can, and this metric value spin distribution can be parameterized in the unpolarized and the polarized part. This is unpolarized phase space distribution, and this is a polarized spin polarization distribution. Well, this is NJ. J is 1, 2, 3. Actually are 4 vectors of the 3 basis directions in rest frame of Q and Q bar, and 1 is the spin quantization direction. And here is the tau is the Pauli matrices. And in terms of this metric value spin distribution function, you can derive the spin Boltzmann equation with the Cauchy term. For example, you can decompose the Boltzmann equation into 2 parts. One part is involve this scalar part, is give you the unpolarized distribution. The another part is the related to the polarized part. By solving this spin Boltzmann equation, then you can determine the F0, the 0th order, because we make expansion in terms of the Planck constant. Once you get this F0, this at 0th order, you insert, you can solve the distribution function, the metric value distribution function at the 1st order in the Planck constant. You can solve this metric value distribution function order by order in the power of the Planck constant. Okay, so then I switch to the spin alignment of vector mesons. In order to describe the spin alignment of the vector mesons, we need a spin Boltzmann equation for vector mesons. Okay, so here is the first measurement of the star of the global spin alignments of the vector mesons. You can see this, the rho 0, 0 is a 0, 0 component of the spin density matrix, which is called the spin alignment as a function of the collisional energy. For phi meson, you can see it's a rho 0, 0. There's a large deviation, which is indicating the large spin alignment of the phi meson, while the rho 0, 0 for the k star 0, another vector meson, which is consistent with the 1/3, which indicates that there's no global spin alignment for the k star 0. So this experiment implies there's a strong correlation or fluctuation between the PS and PS bar forming the phi mesons. This indicates that PS and PS bar, the average value of PS and PS bar is not, or is much larger than the products of the PS average and PS bar average. Now, so this is a very strong implication for this PS bar average value, much larger than PS average value times the average value of PS bar. So indicate a strong correlation in PS and PS bar. Okay, so this, in order to, I think the picture is like this. We want to derive the relativistic spin Boltzmann equation with collision term for vector meson with this quark coalescence model. And then the picture is simple. When at the time of hydrogenization, where in which the S and S bar form a phi meson, they will polarize, both S and S bar should be polarized by some vector field. So like an electromagnetic field, but it's a massive vector field. The field that polarizes S quark is the same as the field that polarizes S bar. So therefore, there's a correlation between these two fields, so which gives the rho 0, 0, deviation of the rho 0 from the 1/3. So this is the basic idea. Then, in order to derive the spin polarization for the to describe the spin alignments of the vector meson, we need to make use of the width function, which is defined through the g mu nu less. This is a 2-point function on the Schwind-Kaddish formalism. Then it is defined as the 2-point a located as x1 and a another is located at x2, then you can make a Fourier expansion, or Fourier transformation with respect to the difference between x1 and x2. Then you get this. In Monod space, it is related to the metric value distribution function for vector mesons, f, lambda 1, lambda 2 are spin states. How much time? So 30 minutes. 10 minutes, okay. So then using this, making use of this spin-dependent distribution function for vector meson, then you can really derive the spin-Boltzmann equation with collision term for vector meson. This looks like this. And this f lambda 1, lambda 2 are metric value spin distribution function for vector mesons. And this is a collision term, the coalescence term in the collision term, and this is the dissociation term in the collision term. You can see that you can a schematic formal solution of this is proportional to the coalescence kernel divided by the dissociation kernel times a function. Okay, so the spin structure of this metric value spin distribution function is mainly controlled by the coalescence kernel. So the coalescence kernel, just like this, you can see this FQ is the unpolarized anti-quark distribution function, and this is a quark distribution function, and this is a delta function to guarantee the energy conservation for this coalescence process, and this is a polarization vector, and this is a PQ and PQ bar are the polarization vector induced by the effective phi field, a kind of a strong force vector field. Okay, so then you get this formula. In the rest frame of the vector meson, this 0, 0, 0, 0 is related to the B part and the E part. Prime, all the fields with prime are the fields defined in the rest frame of the phi meson. And you can express the same 0, 0, 0 in terms of the field in the left frame. Then you can compare with data. Here is the these two curves are the result of our model based on the parameter ft square, fz square, the transverse field square, and the longitudinal field square extracted by the data. Then you can show this. It matched the data. For the in-plane, this outer plane data, this is the in-plane data. And with these parameters, ft square, fz square, you can describe many things. For example, you can describe the transverse momentum spectrum of the 0, 0, 0. This is 11 GeV, 20 GeV, 27, 39, and this is 62 and 200. The shaded area is the error when we extract the two parameters, ft square and fv square from the data. Okay, so this is our prediction for the 0, 0, 0, 0 as a function of the rapidity. If we assume that the b square and e square is isotropic in all directions in the left frame, then we have a very simple formula with a clear physics of 0, 0, 0 deviation from the of the 0, 0, 0 from 1/3. It's I think dependence of the y is coming from the pz, which is a sine square y. This is, I think I should emphasize this. This prediction is before the star released their preliminary data in the last quark method. This is our prediction is before this release of the data. Okay, so then why people normally ask why there's the strong force field played a role. I think the answer should be in the chiral quark model in this paper. And you can see at short distance, we know that the degrees of freedoms are quarks and gluon. At long distance, it's a Gaussian boson, right? But in between, in the interface between the perturbative regime and the non-perturbative regime, then in this regime, just the interface, on the interface, there should be Gaussian boson as well as quark and gluons. So therefore, this is people this is Manohar and Georgia proposed the chiral quark model. It is based in that model. SU3 boson can be described by this chi field, which is SU3 pseudoscalar in terms of pi, pion, kaon, and eta. Okay, so then you can write down according to the transformation on the SUL as SUR. You can write down the Lagrangian. This is for the chiral quark model, and the psi is the quark field. Is with a 3 flavor with a color, and this is a V field. V field is vector field. Is induced by the current of this C field. C field is the SU3 boson field. You can see the current will induce the vector field. Also, you can combine from the different symmetry. You can combine the pseudo. This is the actual vector field, A field. Then then we can conclude that the effective vector field can be induced by the currents of the boson field. Okay, so then you can derive the equation motion for the vector fields produced by the quark currents. You see this is the quark currents, and TF is in favor gamma matrices. And then you can see by solving this VA, the A is the flavor indices. Freedom index, which is correspond to the 8, 1 to 8. So the flavor SU3 vector meson multiply can be expressed in this by this matrix. You can see once you solve this VA, then you can get the rho field, rho plus field, rho minus field, K plus field, K star plus, and K star minus. Also, you can get the K0 and the K bar 0, and you can get the rho 0. So all these vector fields, you can get the fields by solving this equation motion for the vector fields. Okay, so then the picture which I showed before, then the vector field that polarized S quark is the same as the vector field that polarized S bar. There's a correlation between these because they are the same field. But what happened for the K star 0, which is carry the net flavor? So this is involve the two vector field. One, you can see the S quark. Then this is D quark, maybe D quark or U quark. But for the D quark, it's a kind of a K star. This is K star 0 and K star bar 0. So involve the two kinds of vector field. They are correlated in the play the role in the spin alignment of the K star 0. Okay, so then I think I should stop. The take-home message is that P lambda measure the fields, net mean fields, while the rho 0 for phi meson measure the field squared, the field correlation or fluctuation. Then the vector strong field is induced by the current of the pseudoscalar boson, pseudo boson boson during the hybridization. I think there's many open questions. I will not read it. Thank you very much. Yes. I think this because they are fluctuating. If you measure the field itself, it should be 0. It's fluctuating. Yeah, but if you measure the coloration or fluctuation of this field, they should be there. So rho 0, the spin alignment of the vector meson, just to measure the coloration. Yeah. Yes, I cannot see except the rho 0. Rho 0 is just a manifestation of this fluctuation of the field. Yeah, exactly. No, this field is, I mean, fluctuation. This is always fluctuating. The net effect is 0. They're local. It's local. It's not global. It's local. When the S quark and combine with S bar, at that time, there's a field takes effect. Polarized. The field polarized S quark is correlated. It's strictly correlated with the field that polarized S bar. Yeah, yeah. So I cannot see any other observable which is related to this field fluctuation or field correlation. I don't know. Up to my knowledge, I don't know any other.
Perhaps I would expect that we have some possible spectra. So the way they have some interaction which matters as near the freeze out, near the particular then you should fit something in the spectra. Hydrogen gas, the Cooper formula.
Yes, yes, yeah.
There are some, say, some methods like in practice it is just free hydrogen gas. Whereas if you have a role of interaction, like in this case, that we would expect, perhaps we would expect something not just in polarization, but in the spectrum.
But I mean, they are highly fluctuating field at the time of hydrogen, highly fluctuating field. Yeah, I think the correlation. Yeah, I think to my knowledge, rho 00 is the only observable which can measure the correlation in such a kind of fields. No other. I don't know other. But maybe it has some effect on the spectra, but people cannot pin, it's very hard to pin down.
We have we got used to the paradigm of the strong interaction where quarks and gluons near the physical temperature that not essentially play any role because we cannot, in a sense, we cannot take any kinetic picture because the interaction is so strong that you cannot think of a system of weakly colliding particles.
Yes.
How can this idea coincide with a picture where first polarize quarks and then we recombine them?
Yeah. This is I think this question exists always exists for the coalescence model. The coalescence model is the hadron is formed by quark, right? So yeah, this quark is not current quark; it's addressed quark. It's a constituent quark. There's a strong indication that the hadron is made of coalescence, made by coalescence, because we have seen in the Rick experiment. They show that the coalescence mechanism is the dominant mechanism. Yeah. Yes. Oh, of course. But also, this is a softer physics, purely softer physics, because yeah. Yeah, soft particle. It's a constituent. Isn't yeah.
Thinking about how does this reconcile with the picture that we have been used to of a strongly interactive fluid where you can, which cannot be described in terms of other particles colliding with
yes, yeah. Maybe you can treat the. I mean, if this mechanism, the coalescence mechanism is one mechanism for the hydrogenation. Another mechanism that can polarize this phi meson spin alignment, lead to the spin alignment phi meson is a shear stress tensor. We also calculate it, but it's small. We also calculate this. So the shear induced spin alignments for the delta rho 0. We can show that it's very small. Yeah. If you count this, take this simulation, the magnitude of the shear stress tensor into account is a small effect. Yeah. So the C is the coefficient, tensor coefficient coupled to the shear stress tensor. For example, it's you can see it's 10 to the minus 3. If you multiply this shear stress tensor, also normally it's in the 10 to the minus 2. It's a 10 to minus 4. Using the linear response theory. So linear response theory give you can calculate the shear induced spin alignment. This is in this paper. This paper. Yes, yes, yeah. I don't have time to talk about this. Yeah. Yeah. Yes. And also, it's which give us a little bit confidence in that this prediction give us a little bit confidence about our model. This just just before last quark meta conference, we were asked by the experimentalist to make this prediction, rho zero as function of the rapidity dependent. Then we use the same parameter extracted from our previous work to get this to get this curve. So the curve is matched with the. It turned out that's a match with the data, but at that time we don't know the data at all, and the experimentalists didn't know what we predict. So then it turned out that it's a match. The behavior, at least the behavior we predict. Yeah. Yes, it's related to hydro. This is a shear induced, but this it turned out this is not large, not large. Yeah. But anyway, you can try. You can take a try. Yeah, exactly. Yeah, of course. Yeah, yeah. From the shear. Yeah. Yeah, we use the same method, but we get calculated. It's really calculated this coefficient, but they didn't. They just set up some framework to calculate. But we use the same method. We should use the linear response theory. Yeah, to get this linear. For example, if you do not use this method, linear response theory, you cannot get this C linear term. You get zero if you assume the thermal equilibrium. Yeah, it's zero. It's a zero. It's zero. This coefficient is zero in the linear order, but the lowest order is in the quadratic order. Yeah. Oh, okay. Yeah, I see. Your work. Yeah, I guess you get this coefficient. You calculate the coefficient, but without yeah. Yeah, exactly. Yeah, I know this. You use hydro, spin hydro, to get this coefficient, but we use the linear response theory. Yeah, same as Shuai Liu and Feng Li, that paper. Same as this. Or spin kinetic theory. Yes. Collision term. You mean the vector meson? Fermions. Okay. This. Yeah. Yes, yes, maybe, yeah. I think it's a very good idea. So you can estimate the B0 on that model, in that model by this theory. Yeah. Yeah. But this is based on the model, collision term based on model. You use NGR model, for example, you get the quark scattering. Oh, yeah. That's a good idea. Yeah.
I can see you agree everything of theory and people do it because is there any hope for lattice QCD?
Oh, it's a lattice QCD. I don't know. I have no idea because this is a dynamic. This is dynamic effect. Yes. You mean using lattice QCD, right? But this, I would say, I don't know, I have no idea, because the lattice normally you assume the Euclidean space, but here is purely dynamic. The time is explicit.
Polarization has not been calculated originally by you, but by using just around. I know, I'm thinking about the idea of you can do it with kinetic theory, but you cannot do it. The question, second question about, as far as I know, that there are some, there is a very good working on rotating lattice QCD on with angular velocity. Yeah. Loosely speaking, the rotating phase. And they have some results. Some of them are really interesting.
Yeah. Yeah, there's a lot of people doing the lattice in the rotation frame, lattice with rotation. Yeah.
But in general, there is the issue that we have the sign problem also when producing calculator. Yeah, velocity.
Yeah. Okay. Thank you very much.